Given a simply supported beam with uniformly increasing load from B to A, and we are also find for the shearing force and the bending moment diagram, the calculations and all other things like that. So now, how do we solve that kind of question? So first of all, we know that in a simply supported beam, the first thing we look for is our reaction or reaction at A and B. So now looking for our reaction at B, our reaction at B times the total length A will be equals to the bending moment of this uniformly increasing load. And for a uniformly increasing load, take note that we have to take note that a uniformly increasing load, the shearing force, the shearing force of a uniformly increasing load is the area of the triangle, like the area of the section of the triangle in which you are dealing with, which is half base times height. And the bending moment here would be this shearing force right here, the shearing force times the distance from the centroid, that is the centroidal distance, that is the shearing force times the centroidal distance. So the bending moment is what we are looking for here. So we have the shearing force times the centroidal distance, but the shearing force is the area. So now looking at the area, we have 1/2, that is half. What is our base? Our base is this entire length here times L times what is our height? At the total edge here, the height is W, but at a point X here, the height will be given as W times X over L. So we are given this. So therefore, this is the bending moment. This is the shearing force. So after this times the centroidal distance. So now, what is the centroidal distance? In a uniformly distributed load, right here, which is something like this, the centroidal distance is at the center. It just acts like a rectangle. The centroidal distance YY would be at the center. But if we have a triangle, the centroidal distance will be somewhere here, which is 1/3 of the total distance x. That is 1/3 of the total distance x. So that is times 1/3 of the total distance l. That is what it will be. So it will be equals to 1/2 times that is 1 over 6, 1/6 times WL square, that is WL square over 6. So that will be RB times L is equal to WL square over 6. So if you divide both side by L, we have our RB to be equals to WL all over 6. So right here, our RB our RB is equals to WL over 6. So we are getting our RB. And for our RA, we know that our RA is equals to the total shearing force minus the reaction at B. And we know that the shearing force is half base times height, which is 1/2 L times W. So we have WL over 2 minus our RB, which is WL over 6. Collect like terms, we have 6, then it will be 3WL minus WL, which is equals to 2WL over 6. 2 here 1, 2 here 3 is equals to WL over 3. So therefore, our reaction at A is WL over 3. So these are our reactions at A and B. So now, the shearing force, we are asked to find for the shearing force. The shearing force now, the shearing force at B here would also be equals to the reaction at B, which is equals to WL over 6. And the shearing force at X, which is this point here, let me bring it out. Let's say this is where one section here, this is X, and we have this out here, something like this. This is the this is the section here with distance x from here to here. So and we also have, don't forget that we also have reaction B here. We have reaction reaction B from here. And this total height is Wx over L. That will be the height of this. So if we are to calculate the shearing force of this triangle here, we have 1 over 2 times, what is our base? Our base is x times, what is our height here? Wx over L. So at the end of the day, we will have it as Wx square all over L. That is for the top triangle. That is for the top triangle. So the total shearing force here now would be equals to this RB here, and this RB is WN over 6. So we have WN over 6 minus this one here, which is Wx square over L. That will be the shearing force from here, Wx square over L. So this will be our shearing force, not over L, this over 2L, over 2L, because this 2 times L is equal to 2L. So it will be equal to WL over 6 minus Wx square over 2L. That will be the shearing force at X. So now our shearing force at A would also be the reaction at A, but it will be negative. So it will be minus WL over 3 in kilonewton as usual. So now we know that in this diagram is going to be a cubic curve, the bending moment. So then we are going to need to find for the highest point in the cubic curve. So and we know that the highest point in the bending moment is usually the point whereby the shearing force is equal to 0. So now if the shearing force of x is equal to 0, what is the what will be the value of x? So we have Wn over 6 minus Wx squared all over 2n is equals to 0. What is the value of L? So now, if we are finding for the LCM of this, we are going to get 6L. So 6L divided by this, we have L, we have WL squared minus 6L divided by this, we have 3. 6L divided by this, we have 3. That's 3Wx squared. 3Wx squared. So that is equals to 0. If we do cross multiply, it will cancel the bottom and we will have it as WL square minus WX square is equals to 0. W is common here, so bring out W, open bracket, L square minus 3x square, then we close our bracket, is equals to 0. Divide both sides by W, W cancel W, so 0, that is equals to L square minus 3x square will be equals to 0. So we collect like terms here. We have minus 3x squared is equals to minus L squared. So then divide both sides by minus 3. Minus cancel minus 3 cancel minus 3, minus cancel minus 8. So we have x squared is equals to L squared over 3. Then we find for the square root of both sides. So this square will cancel this square here, this square root will cancel one square here, and here we have x is equals to L over the square root of 3. So x is equals to L over the square root of 3 is the point whereby the bending moment is the highest. So we have the s of f of 0, that is where x is equals to 0, is equals to L over the square root of 3. So with that, we should be able to get our bending moment maximum. So now, our bending moment calculation, the bending moment at B is equals to 0 because there is no movement at all. Then our bending moments at x, at this point x, what will it be? So our bending moment at point x here would be this rb, which is rb here is given as wl over 6 times the distance. So we have wl over 6 times x, then minus the shearing force of this one here, which is wx, we have this as w, we have ws square over 2n, which is the shearing force, times the centroidal distance for here, which is times x over 3, which will end up giving us wnx over 6 minus wx cube over 6n. So that will be our answer for the bending moment at point X. And our bending moment at point A is 0, but we are looking for our max bending moment now. So our bending moment at the max point, that is where x is equals to n over root 3, what will it be? That is, whenever we see x here, we put n over root 3. We will get wn over 6 times n over root 3. Then we have minus w over 6n. We have x cube here, so it will be n over root 3, then we cube it. So if we continue, we have wn square over 6 root 3 minus here, this 6n here, this is n here. We have w over 6n times n cube over what is 3 cube? 3 cube is equals to 27 over square root of 27. And we know that in according to sod, if we have square root of 27, we can bring it out as 27 is equals to 9 times 3. So we have square root of 9 times 3, which is square root of 9 times square root of 3, which is equals to 3 root 3. So this one can be represented as is equals to wn square over 6 root 3, which is this one, minus, now this n here would cancel one n here, remaining 2. So we have wn square all over this our 6 here times, we have our 3 root 3 times 3 root 3. So we will get our bending moment, our max bending moment, as we have wn square over 6 root 3 minus wn square over 6 times 3, we have 18 root 3. So now we have two similar values here. We have wn square over 6 root 3, then minus wn square over 18 root 3. If we find for the LCM between 6 and 18, we do like 6, 18, 3 here, 2, 3 in 18 minus 3 in 18 is 6, then we have 2 here, 2 here 1, 2 here 3, we have 3 here, so right here we have our LCM to be 18 root 3 right here as our LCM. So since I got our LCM to be 18 root 3, 18 root 3 in this, it will be it will be 3. So we have 3 times W L cube minus a single 3 in this, that is 1, that is this WL, is it cube or square? Is WL square minus, here we have WX cube, WX square minus WL square over 18 root 3. So from here is equals to 2WL square over 18 root 3. 2 here 1, 2 here is 9. So we have WL square over 9 root 3. So that our P max is equals to WL square over 9 root 3. So that will be our B max, the bending moment at the maximum point, WL square over 9 root 3. And our bending moments at A will be equals to 0. So since we have gotten that, value, we proceed to draw our diagrams. Then yeah. So we proceed to draw our diagrams. So from the shearing force, we have our neutral line here. Our shearing force at B is WL over 6, something like this. Our shearing force at A is WL minus WL over 3, something like this, which is also something like that. So it's going to go this way. We have something like this. Let's say this. So from here to here, this is WL over 6, and here is WL over 3, negative and positive. And the shearing force at point X here would be WL over 6 minus WX square over 2L minus WX square over 2L. So that would be the value right here. So now this is the shear force diagram. To the bending moments diagram, you have the bending moment diagram. From these points right here, where the shearing force is 0, is the point whereby we are going to have the highest bending moment. So drawing the bending moment diagram is going to be something like this. It's going to be something like this, whereby this point right here is where we have our WL square over 9 root 3. This is 0 and this is 0. And the bending moment at X right here, this one is WLX over 6 minus WX cube over 6L. So that will be our value. That will be our value for our bending moment diagram and our shearing force diagram.